Okay, today this is our last lesson. This is our last lesson, and I think after this I will give some grades. I will give some grades to all of the students, and now we are going to do some more exercises. To do some more exercises in electrical oscillations. Electrical oscillations. So let's do this. Let's do this. And the first exercise is number 11. Number 11. Number 11. There are oscillations with energy W, energy W in a LC circuit that consists of a parallel plate capacitor and an inductor. What work was done when the plates of the capacitor were moved apart from each other if the frequency of the oscillations increased eta times? Or maybe I'll draw a scheme of this circuit. So we have LC circuit. LC circuit consists of inductor, inductor, inductor and capacitor. Inductor and capacitor. Inductor and capacitor. Inductor and capacitor. We have such circuit. We have such circuit. This is capacitor and inductor. Okay, maybe you have some ideas. How to solve this exercise. Okay, So we have energy of oscillations. We have energy of oscillations. This is initial energy, and then the distance between plates of capacitor. The distance between plates of capacitor was increased eta times. Was increased eta times. So plate separation was increased. Plate separation was increased. So how to the question is how to connect energy with parameters of this circuit. We need to have some dependence between parameters of circuit and energy, and then we need to connect these parameters with plate separation of capacitor. So how can we write this dependence? First of all, I mean this energy. But I mean energy. I don't mean frequency. Because frequency is equal to one divided by square root of LC. Okay. Okay, we have this. We have this. We have this. We have this. But what about energy? This is energy. It is necessary to remember. It is necessary to remember our lectures. To remember our lectures and remember the formula for energy of capacitor. Maybe formula for energy of inductor. We have oscillations. We have capacitor and inductor. It means that energy may be equal to maximal energy of capacitor. Maximal energy of capacitor can be written in this way. It can be written in this way. When all energy of oscillations is in capacitor, we have this formula. But after this, during oscillations, this energy goes from goes from capacitor to the inductor, and after this, energy will be in the inductor. Will be in the inductor. Will be in the inductor. And some intermediate case, when part of energy is in capacitor and part of energy is in inductor, can be written as this. Plus divided by 2. Divided by 2. Okay, do you have any questions about this? No questions. Okay, so which of these do we need? Which of these do we need? This or this or this? All of these expressions are true, but we need only one of these. Okay, of course we need this. We need this. We need first formula. So we have some initial energy of oscillations is maximal value of the charge on capacitor divided by its capacitance multiplied by 2. And after changing of plate separation, after changing of plate separation, we have energy that can be written in this way. Okay, so the next question is what to do with C1. How can we get this? How can we get C1? No idea. But according to the condition, when the plates of the capacitor were moved apart from each other, frequency increased at times. So frequency was omega 0. Natural frequency was omega 0. It was omega 0. but after changing in plate separation, it has become some omega 1 divided by square root of LC1 Okay, so from here we have that from here we have that eta is equal to uh, omega 1 divided by omega 0. This is according to the condition. And here we have that square root of LC1 divided by square root of LC, and this is equal to CLC1, and this will be C divided by C1 divided by C1 okay. Do you have any questions about this? Do you have any questions? So from here we can write that 1 divided by C1 is equal to eta to the power of 2 divided by capacitance. Okay, do you have any questions about this? No questions. Okay, so according to the condition, we have to find work that was done when plates of the capacitor were moved. Work that was done. So we need to find work. How to do this? How to find this work? Do you have any ideas how to find work? I can give a little advice. We have energy. So how to connect? Energy and work? Energy and work. We can write that work according to the law of energy conservation. According to the law of energy conservation, it is equal to change in energy. It is equal to change in energy. So we can write that it is equal to change in energy. So this will be UV to the power of 2 divided by 2C minus 2C1 minus UV divided by 2C. And I will use this. Eta to the power of 2 Q minus QV divided by 2C. And this is we can use this formula for energy again, and according to this we have minus double V. So we have eta to the power of 2 minus 1 double V. So work is equal to eta minus 1 double V. Okay, this is the answer. This is the answer. This is the answer. So, do you have any questions? Do you have any questions about this? No questions. No questions. Okay. If there is no questions, let's do the exercise number 12. Exercise number 12. Exercise number 12. I need to clean this. I need to clean this. I need to clean this. Number 12. Number 12. According to the condition, a LC circuit consists of a capacitor with capacitance C and an inductor with inductance L. The coil is in constant magnetic field with flux linkage phi. At a moment in time, t is equal to 0. At a moment in time t is equal to 0, the magnetic field was turned off. Assuming the time of magnetic field turning off is negligibly small in comparison with natural period of of the circuit. Find the current in the circuit as a function of time. Find the natural period of circuit. No. Find the current in the circuit as a function of time. So we have to find current. We have to find current in this circuit. Current in this circuit. Okay, do you have any ideas how to do this? We have two elements. This and this. So we have inductor or induction coil and capacitor. So according to the Ohm's law, we can write that we can write for this circuit that electromotive force of self-induction is equal to voltage across the capacitor. Voltage across the capacitor. So the question is how to write this. And voltage across capacitor. So this is electromotive force of self-induction in the inductor. So we need to remember formula. For this. So how can we write this? But the formula is simple. It is Faraday's law of induction. According to Faraday's law of induction, we can write that this is equal to minus inductance multiplied by first derivative of current. Okay, and what can you say about current? What can you say about current? How to yeah, this is according to the definition. Okay, according to the definition of current, we can write that this is the first derivative first derivative. And according to this, we can write that this will be, maybe it is necessary to write this here. According to this, we can write that this will be minus L d to q divided by d to q dt to second derivative of charge by time. Okay. Okay, and what about voltage across the capacitor? Voltage across the capacitor. What about this? Yes, this is a charge of the capacitor divided by its capacitance. Charge of the capacitor divided by its capacitance. Okay, so we can use this. We can use this to build differential equation. To build differential equation, so we have minus L d2 q divided by dt to the power of 2 to the power of 2, and this is equal to q divided by c. Q divided by c. Okay, and from here we have that this is equal to d2q divided by dt to the power of 2 plus 1 divided by L C U, and this is equal to 0. This is equal to 0. And finally we have differential equation. Differential equation. dt2 plus omega 0 to the power of 2 multiplied by q. And this is equal to 0. Where omega 0 is natural frequency, and this is equal to 1 divided by square root of LC. Square root of LC. Okay. Okay. And how can we solve this differential equation? How can we solve this differential equation? It is necessary to remember its a solution from our lectures. Our last 4 lectures were devoted to were devoted to solutions of differential equations of small oscillations. And we have solved all of them. We have solved all of them, so it is just necessary to remember the solution. Remember the solution of appropriate equation. I mean this. That electric charge U is equal to UV, amplitude of electric charge, multiplied by cosine omega 0 t plus alpha plus alpha. And from here we can find electric current. Electric current is dq by dt and this is equal to minus qv sinus no sinus omega 0 sinus omega 0 t plus alpha. And this is equal to q no, sorry, uv. This is maximum value, uv omega 0 cosine omega 0 t plus alpha plus p divided by 2. And this can be written as IV, amplitude of the current, cosine of omega 0 t plus alpha plus p divided by 2. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, let's clean some unnecessary information. Let's clean some unnecessary information from the screen. So I will clean this. I will clean this and this. So
Teacher, how does this go to this step?
it is according to the trigonometric formula. Okay, maybe let's write this. Let's write this more particularly. Let's explain this. It is necessary to clean some. It is necessary to clean some place. It is from. It is a trigonometric formula. For example, can you remember this formula? Cosine of alpha plus beta is equal to cosine alpha cosine beta minus sinus alpha sinus beta. Can you remember this? Maybe from school, from...
Yes.
Okay. Okay, so let's try to use this formula. Cosine of alpha plus p divided by 2. So this will be cosine of alpha, maybe cosine p divided by 2 minus sinus of alpha sinus of p divided by 2. Okay, so from here we have cosine of p divided by 2. This is equal to 0. This is equal to 1. So we have minus sinus alpha. Minus sinus alpha. So from here we have obtained that's minus sinus alpha is equal to cosine of alpha plus p divided by 2. And I have used this here. I have used this here.
Okay, I understand it. And why QV? Oh, okay, I understand. QV omega 0 equal I. Yes.
Because we have just resigned. We have just resigned this. We have just resigned this as IV. So
Okay.
we have used another symbol to another symbol for this. Or maybe another explanation is that coefficient near cosine is an amplitude. So Here coefficient near cosine is an amplitude of electric charge, and here coefficient near cosine is amplitude of electric current. Amplitude of electric current. Okay, so let's continue. Let's continue. How can we find to finish this exercise? We have to find this and this. This and this. How to do this? I think we can find them from initial conditions. From initial conditions, we can find them from initial conditions. According to this, at a moment in time t is equal to 0, magnetic field was turned off. Magnetic field was turned off. So we need to remember dependence between the flux linkage and current. Dependence between flux linkage and current. So how can we connect flux linkage with current? It is formula from electricity and magnetism. Formula from electricity and magnetism. We have learned this. This can be written as L inductance multiplied by amplitude of the current. So from here we have that IV is equal to P divided by L. Phi divided by L. P divided by L. Okay, and what about alpha? If at some moment of time, at a moment in time t0, electric current was maximal, it means that electric charge was equal to 0. So from here we can write that Q when t is equal to 0 is equal to Q V cosine cosine alpha, and this is equal to 0. This is equal to 0. Okay, and how can we find alpha from this? How can we find alpha from this? Okay, this maybe. I think we need a general solution, so we can write plus p k, where k is integer. K is any integer number. K is any integer number. So it means that alpha may be equal to plus or minus p divided by 2, or plus or minus 3p divided by 2, or maybe plus or minus 5p divided by 2, and etc. Okay, so we can use any of this. So any of these. We can use any of these. But the most useful is alpha is equal to minus p divided by 2. This is the most useful, because here we have alpha plus p divided by 2. So we can write that if we choose this solution, we can write that I, electric current, is equal to IV cosine omega 0 t plus alpha plus p divided by 2, and this is equal to let's write phi divided by L, inductance divided by L, cosine 1 divided by the square root of L C T minus P divided by 2 plus P divided by 2. And finally we have phi divided by L, P divided by L, cosine T divided by square root.
Teacher, here why does it be minus?
Sorry, plus
Okay.
LC. 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 Okay, this is the answer. This is the answer. Okay, so do you have any questions? No questions. No questions. Okay, if there is no questions, let's try to do number 13. Number 13.
Teacher, why here we should get the value minus pi divided by 2?
Uh, just just to make the answer more simple. Just to make the
Okay.
answer simpler. Because it is useful. It is useful because here we have minus and plus p divided by 2, and the answer will be the simplest in this case.
Okay, I get.
But we can use any of these answers. Any of these answers, but final result will be more complicated in other cases. Okay, and the next is number 13. Number 13. Number 13. Number 13. In a RLC circuit with capacitance C and inductance L, capacitance C, inductance L, capacitance C and inductance L. We have RLC circuit, so we have to modify our picture to take into account resistance. Take into account resistance. We have to modify our circuit. So in a RLC circuit with capacitance C and inductance L, there are three damped oscillations with not circuit, with current. With current. There is a typo in a condition. Typo in the condition. So not circuit, current. Current that changes in time according to the law. According to the law, E is equal to I M. Maybe it is better to write IV. It is better to write IV e to the power of minus beta t sinus omega t. Find the voltage across the capacitor as a function of time, and in particular at a moment of time t is equal to 0. Okay, do you have any ideas? Do you have any ideas how to do this? Okay, maybe let's build a differential equation. So here we have three elements that are connected in series. Three elements: inductor, capacitor, and resistor. So let's let's use Ohm's law. Here we have capacitance, electromotive force of self-induction, and this is equal to voltage across resistor plus voltage across the capacitor. Okay, maybe you can remember this. Maybe you can remember this. Uh, Cannot remember. Okay. We have just used this. We have just used this in previous exercise. No. Okay. It is minus. Okay. 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 Yes. This is minus L multiplied by first derivative of electric current. First derivative of electric current. First derivative of electric current. Okay, so we have first term. Okay, and what about voltage across resistor? Uh-huh. R dq by dt. Okay, 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 but in this case, it is better to remember. It is better to remember that I is equal to dq by dt. It is better to remember this. It is better to remember this. And according to this, we have that this is equal to R multiplied by I. In this case, this will be more useful. This will be more useful in this case. So from here we have that voltage across the capacitor, is equal to ES minus UR, and this will be minus L di by dt minus R I okay, and from here we can write that this is equal to minus d, no, sorry, minus L d I by, no, di d by dt I v e to the power of minus beta t sinus it is better maybe to write here omega v. Yes, so maybe I will make some changes in these conditions of exercises. IV, it is better to write IV. I think it will be better. It will be better in this case. So we have and minus R I V e to the power of minus beta t sinus omega v t. Okay, let's find the derivative. It will be L beta IV e to the power of minus beta t minus beta t sinus omega v t minus L omega v electric current, amplitude of electric current e to the power of minus beta t sinus cosine of omega v t, and minus resistance IV e to the power of minus beta t sinus omega v t. Okay. Okay, this is almost what we need, but how to find the resistance? How to find the resistance? How to find the resistance? Okay, no idea. According to the condition, we have a formula for electric current. We have dependence of electric current on time from the condition of the exercise, and in this formula we have beta. Where beta is damping coefficient. And we can remember. Yes. Yes. Okay. We can use this. We have that beta is equal to R divided by 2L. Yes, and from here we have this. From here we have this. From here we have this. Okay. So let's use this formula here, and we can write that this is equal to L beta IV e to the power of minus beta t sinus omega v t minus L omega v I v e to the power of minus beta t cosine omega v t cosine omega v t and minus 2 L beta IV e to the power of minus beta t sinus omega v t. And this is equal to minus L I v e to the power of minus beta t minus beta t. It will be beta sinus omega v t plus omega v cosine omega v t. Okay. Do you have any questions? Do you have any questions about this? No questions. No questions. Okay. Okay. If there is no questions, let's continue. I will clean some information. I will clean some information from the screen. I will clean some information and I will leave just a final result. I will leave just a final result. So beta t we have here. I will leave just final result. Okay, and from here we can say that u c when time is equal to 0 this will be minus L I v minus L I v omega v omega v omega v. Okay, do you have any questions? Do you have any questions about
No.
this? No. Okay, so That's will be all for today. That will be all for today. Okay, so thank you for your attention. Thank you for your attention. It was our last lesson. It was our last lesson. I will write. I will write in Telegram. I will write in Telegram table with grades. Table with grades. So thank you. Thank you for your attention.
Thank you, teacher. Have a nice weekend.
See you, teacher.
Goodbye.
Yay.